Welcome to this video. Today, we'll be tackling LeetCode problem number 1217, minimum cost to move chips to the same position. This problem challenges us to find an efficient way to align chips located at various positions on a number line, while minimizing the cost. Let's dive in and explore the solution. In this problem, you are given an array called position, where each element represents the position of a chip on a number line. Your goal is to move all the chips to the same position while minimizing the total cost of movement. The movement rules are as follows. If you move a chip between two positions that are either both even or both odd, the cost is 0. However, if you move a chip from an even position to an odd position, or vice versa, the cost is 1. For example, moving a chip from position 2 to position 4 costs 0 because both are even, but moving a chip from position 2 to position 3 costs 1 because one is even and the other is odd. Ultimately, the task is to calculate the minimum cost required to gather all chips at one position. The input will be an array with up to 100 elements, where each element is a positive integer as large as 10 to the power of 9. Your output will be a single integer representing the minimum cost. Let's look at an example to clarify this problem. Suppose the input array is position equals 1, 2, 3. To minimize the cost, we can move the chip at position 1 to position 3 with a cost of 0 because both positions are odd. Now the positions become 3, 2, 3. Next, we move the chip at position 2 to position 3, which costs 1 because position 2 is even and position 3 is odd. Adding these costs together, we get a total cost of 0 plus 1 is equal to 1. The output for this example would be 1. Here's another example. If the input array is position equals 2, 2, 2, 3, 3, we can move the chips at positions 3 and 3 to position 2. Since moving from an odd position to an even position costs 1, each of these movements contributes a cost of 1. The chips at position 2 remain in place because they are already at the target. Adding the costs, we get 1 plus 1 is equal to 2, so the output in this case is 2. Now consider an edge case where the input is position equals 1 billion. Here, we can move the chip at position 1 to position 1 billion with a cost of 1 because one is odd and the other is even. The total cost for this input is simply 1. Finally, let's review some important constraints and edge cases. The number of chips, or the length of the position array, can range from 1 to 100. Each position value can be as large as 10 to the power of 9, but this does not affect the solution because the cost depends only on whether the positions are odd or even, not their magnitude. If there is only one chip, no movement is needed, so the cost is always 0. Similarly, if all chips are already at the same position, the cost is 0. If all positions are either even or odd, the cost remains 0 because all chips can align without any cost. However, if the positions are a mix of even and odd, the optimal strategy is to move all chips to the parity group either even or odd that has fewer chips, as this minimizes the total cost. This ensures the solution is both efficient and correct. To solve the problem of minimizing the cost to move all chips to the same position, we can consider a few approaches. The first and most straightforward method is the brute force approach. The intuition here is to try every possible target position and calculate the cost of moving all chips to that position. The cost for moving a chip depends on the parity of the positions. If a chip moves between positions with the same parity, such as even to even or odd to odd, the cost is 0. However, if a chip moves between positions of different parity, the cost is 1. By iterating through all unique positions in the array, calculating the cost for each scenario, and then taking the minimum of these values, we can determine the result. While this approach is simple and easy to understand, it has a time complexity of n squared, as we calculate the cost for all chips for every target position. This makes it inefficient for larger inputs, as the quadratic complexity can quickly become a bottleneck. An optimized approach leverages a key insight about the problem. The cost to align chips depends only on the parity of the positions, not their specific values. Chips can move freely between positions of the same parity, meaning the optimal solution involves grouping chips based on their parity. The steps here are straightforward. First, count the number of chips at even positions and the number at odd positions. Since moving chips within the same parity group has 0 cost, the minimum cost to align all chips is simply the smaller of these two counts. This method has a time complexity of O(n), as it requires only a single pass through the positions to count odd and even chips. Unlike the brute force approach, this method avoids unnecessary calculations and focuses directly on the structure of the problem, making it far more efficient. The optimized counting approach is the ideal solution for this problem for several reasons. First, it is highly efficient, with a linear time complexity of O(n), making it suitable for handling large inputs. Second, it is simple to implement, requiring only a basic counting operation and a comparison, which eliminates the complexity of nested loops. Additionally, this approach is mathematically sound and directly addresses the problem's constraints by focusing on the parity of positions. While the brute force method is intuitive, it becomes impractical for larger inputs due to its computational expense. The optimized approach, on the other hand, achieves the same result with minimal effort and maximum efficiency. No further optimization is necessary, as this method already minimizes the time complexity to the lowest possible level for this problem. In summary, the combination of simplicity, correctness, and efficiency makes the optimized counting approach the clear choice for solving this challenge. In this problem, we are tasked with minimizing the cost of moving chips located at various positions on a number line to the same position. The movement cost depends on the parity of the positions. If a chip moves between two positions of the same parity, meaning both are even or both are odd, the cost is 0. However, moving a chip between positions of different parities, such as from even to odd or from odd to even, incurs a cost of 1. Our goal is to determine the minimum cost required to align all chips at a single position, given these movement rules. To solve this problem, we rely on two main observations. First, moving chips between positions of the same parity is free, while transferring them between positions of different parities incurs a cost. This means that the only calculation that matters is how many chips are at even positions versus how many are at odd positions. The optimal approach is to move all chips to the group either even or odd that contains fewer chips, as this minimizes the total cost. The algorithm consists of two steps. Step 1 is to count the number of chips at odd and even positions. We traverse the input array, checking the parity of each position. If it's even, we increment the even count, otherwise, we increment the odd count. Step 2 is to calculate the minimum cost. Since the cost is minimized by aligning chips to the group with fewer chips, the result is the smaller of the two counts, either even_count or odd_count. The final step of the algorithm is to return the calculated minimum cost. This solution is driven by three key insights. First, the cost is binary, it's either 0 for movements within the same parity or 1 for movements between different parities. This simplifies the problem to just counting odd and even positions. Second, we don't need to worry about the specific position within the even or odd group, as movement within a group is always free. Finally, the fewer chips that need to change groups, the lower the cost, so moving all chips to the group with a majority minimizes the total movement cost. To implement this algorithm efficiently, we use simple data structures and keep the complexity low. First, we traverse the input array to count the chips at even and odd positions, which takes O(n) time. We use two integer counters, even_count and odd_count, to store these counts. This ensures the algorithm uses constant space, or O(1). In terms of complexity analysis, the time complexity is O(n), because we make a single pass through the array. The space complexity is O(1), since we only use two variables for counting and no additional data structures. Let's go through an example to clarify how the algorithm works. Suppose the input is positions equal to 1, 2, 3. We start by counting the chips. Position 1 is odd, so odd_count becomes 1. Position 2 is even, so even_count becomes 1. Position 3 is odd, so odd_count increases to 2. At the end of this step, we have even_count equal to 1 and odd_count equal to 2. Next, we calculate the minimum cost. The smaller of even_count and odd_count is min, 1, 2, which equals 1. Therefore, the output is 1, representing the minimum cost to align all chips at a single position. Finally, let's consider some edge cases. If all chips are already at positions of the same parity, such as positions 2, 4, 6, or 1, 3, 5, the minimum cost is 0 because no chips need to cross parity. Another edge case is when there's only a single chip, like positions equal to 1. Here, the minimum cost is also 0 because no movement is required. These cases highlight how the algorithm handles both typical and special scenarios effectively, ensuring that the solution is robust and efficient across all inputs. This solution tackles LeetCode problem number 1217, minimum cost to move chips to the same position, by leveraging the key insight that moving chips between even positions or between odd positions incurs no cost. The goal is to minimize the cost of moving chips to a common position, which boils down to determining whether it is cheaper to move all chips to an even position or to an odd position. The function min cost to move chips takes the list position, which represents the positions of the chips on the number line. It initializes two variables, even_count and odd_count, to 0. These variables are used to count how many chips are located at even positions and odd positions, respectively. The function then iterates through the position list. For each position, it checks whether the position is even, using the modulo operator POS%2 == 0. If the position is even, it increments even_count, otherwise, it increments odd_count. Finally, the solution observes that the cost to move all chips to an even position is equal to odd_count, since each chip at an odd position incurs a cost of 1 to move to an even position, and the cost to move all chips to an odd position is equal to even_count. Therefore, the minimum cost is the smaller of the two values, which is returned by the function. This approach is efficient with a time complexity of O(n), where n is the number of chips, as it involves a single pass through the position list. The space complexity is O(1), since it uses only a constant amount of additional memory. The implementation is concise and handles edge cases, such as all chips being at even positions, all at odd positions, or a mix of positions, seamlessly. This is the Java implementation for LeetCode problem number 1217, minimum cost to move chips to the same position. The logic mirrors the Python solution, where we count the number of chips at even and odd positions and return the smaller of the two counts as the minimum cost. Key differences include explicit type declarations for variables, the use of Java's enhanced for loop for iteration, and the math.min function to calculate the result. In this problem, we have an array called position where each element represents the position of a chip on a number line. The key is to understand the movement costs. Moving a chip from an even position to an odd position, or vice versa, costs 1 unit, while moving between positions of the same parity, either both even or both odd, is free. Our goal is to calculate the minimum cost needed to move all the chips to the same position. For example, take the input position equals 1, 2, 3. First, we initialize two variables, even_count and odd_count, both set to 0. These will help us track how many chips are at even positions versus odd positions as we analyze the array. Now, we iterate through the positions. Starting with the first chip at position 1, which is odd, we increment odd_count by 1. The current state is even_count = 0 and odd_count = 1. Next, the second chip is at position 2, which is even, so we increment even_count by 1. The state updates to even_count = 1 and odd_count = 1. Finally, the third chip is at position 3, another odd position, so we increment odd_count again. The final state is even_count = 1 and odd_count = 2. To calculate the minimum cost, we simply take the smaller of even_count and odd_count. Here, min 1, 2 gives us 1, so the output is 1. Let's look at another example, position equals 2, 2, 2, 3, 3. As before, we start by initializing even_count and odd_count to 0. For the first chip at position 2, which is even, we increment even_count to 1. The current state is even_count = 1 and odd_count = 0. The second chip is also at position 2, so we increment even_count again, resulting in even_count = 2 and odd_count = 0. Similarly, the third chip is at position 2, so even_count becomes 3. The next chip at position 3 is odd, so we increment odd_count to 1. Finally, the fifth chip is also at position 3, bringing odd_count to 2. At the end of this iteration, the final state is even_count = 3 and odd_count = 2. To find the minimum cost, we compare the two counts. The smaller of even underscore count and odd underscore count is 2, so the output is 2. Now let's consider the input position equals 1 billion. We initialize even underscore count and odd underscore count to 0 again. The first chip is at position 1, which is odd, so we increment odd underscore count to 1. The second chip is at position 10000000000, which is even, so we increment even underscore count to 1. This gives us a final state of even underscore count equals 1 and odd underscore count equals 1. To determine the minimum cost for this case, we take the smaller of even underscore count and odd underscore count, which is min 1 equals 1. So, the output is 1. Through these examples, we can see the key insights of the problem. Chips at even positions can move to other even positions without any cost, and the same holds for odd positions. The cost is determined by the number of chips in the smaller group, either even or odd. By counting these groups, we can directly compute the minimum cost as min, even underscore count, odd underscore count. This approach ensures an efficient solution with a time complexity of O(n). The time complexity of our solution is O(n), where n represents the number of elements in the position list. Let's break this down step by step. First, we iterate through the position list using a for loop. For each element, we determine whether the position is even or odd and update either even underscore count or odd underscore count. Since this operation is performed once for each element, it takes O(n) time in total. Then, after the loop, we calculate the minimum of even underscore count and odd underscore count. This is simply a comparison between two integers, which is a constant time operation, O(1). Combining these steps, the overall time complexity is O(n) for the iteration plus O(1) for the comparison, resulting in a final time complexity of O(n). The space complexity of this solution is O(1), as it uses only a constant amount of additional memory, regardless of the size of the input. Let's examine why. First, the position list itself is provided as input and is not modified or duplicated during the algorithm, so it does not contribute to the space complexity. Next, the algorithm maintains two integer variables, even underscore count and odd underscore count, to keep track of the number of chips at even and odd positions. These variables require constant space, O(1). Since there are no other data structures or dynamically allocated memory used in this solution, the total auxiliary space required remains constant. This makes the space complexity O(1). To better understand the efficiency of our solution, let's compare it with a brute force approach. In the naive approach, we would calculate the cost of moving all chips to each possible position, iterating through the list multiple times. This results in a time complexity of O(n squared, which is much less efficient. In contrast, our optimized solution recognizes that the cost depends only on whether positions are even or odd. By simply counting the number of chips at even and odd positions, we reduce the problem to a single linear pass, achieving a time complexity of O(n). Now looking at the best, average, and worst case scenarios, the runtime remains O(n) in all cases. This is because the algorithm always processes the entire position list, regardless of the distribution of even and odd positions. Whether all positions are even, all are odd, or there's a mix, the runtime is consistently proportional to the size of the input. To formally validate the time and space complexity, we can use a mathematical proof. First, consider the size of the input list as n. The for loop iterates through all n elements, and each iteration involves a constant time operation, such as checking if a position is even or odd and updating a counter. This gives us a time complexity of O(n). The min operation is performed once after the loop and is independent of n, contributing O(1). Adding these together, the total time complexity is O(n) plus O(1), which simplifies to O(n). For space complexity, the algorithm uses only two integer counters, even underscore count and odd underscore count, and does not allocate any additional memory proportional to the input size. This results in a constant space requirement of O(1). Therefore, the solution is optimal in both time and space complexity for solving this problem. One common mistake when solving this problem is misunderstanding how the costs for even and odd positions work. Many assume that moving all chips to any odd position or any even position will always cost the same, but this is not true. What matters is the parity of the positions, whether they are even or odd, and how many chips are in each group. To minimize the cost, you need to calculate the number of chips in both groups correctly. Another frequent error is attempting a brute force approach, where you calculate the cost of moving each chip to every possible position. This is inefficient because it has a time complexity of n squared, which is unnecessary. The parity-based property simplifies the problem significantly, so brute force is overkill. Lastly, some people overlook the fact that moving chips between positions of the same parity, for example, from one even position to another, has zero cost. This is a crucial insight and allows you to reduce the problem to simply counting the chips in the two groups, even and odd, without worrying about specific positions within those groups. Another mistake is overcomplicating the solution. Some solvers use additional data structures like hash maps to track chip positions, but this is unnecessary. The problem can be solved efficiently by just counting the chips at even and odd positions with simple variables. Overcomplicating the implementation only increases the chance of introducing bugs. Ignoring edge cases is another pitfall. For example, if all chips are already at the same position, or if there's only one chip, the cost should immediately be zero. These edge cases are straightforward but can be overlooked during implementation or testing. In interviews, it's important to identify the parity-based simplification early. Once you recognize that the solution boils down to counting the chips in two groups, the problem becomes straightforward. Aim to achieve n time complexity by iterating through the array just once. Be sure to clearly communicate the zero-cost move concept, as this is a critical part of the problem. Also, be ready to discuss edge cases such as a single chip, all chips already in one position, or alternating positions in the input array. There are a few related problems on LeetCode that use similar concepts. For instance, in LeetCode 462, minimum moves to equal array elements 2, you minimize the cost to make all elements in an array equal, and the solution often revolves around medians. This is conceptually similar to the parity-based simplification here, where the grouping matters more than the specific positions. Another related problem is LeetCode 338, counting bits, which explores counting binary parity and even/odd patterns. This problem also requires reasoning about even and odd groupings, though in a different context. LeetCode 453, minimum moves to equal array elements, is another optimization problem that involves minimizing moves, but it uses a different cost model. Finally, LeetCode 55, jump game, is a problem where you also need to reason about positions and how to move efficiently. While it's not directly related to parity or cost minimization, it shares the theme of strategic movement across a set of positions. There are several approaches you could consider, but not all are equally effective. A brute force approach involves calculating the cost of moving all chips to each possible position. While this method works, it is highly inefficient for large inputs because it has a time complexity of n squared. The optimal solution is the parity-based counting approach. Here, you simply count the number of chips at even positions and the number of chips at odd positions, then return the smaller of the two counts as the minimum cost. This approach is both simple and efficient, with a time complexity of n. An alternative method, which involves using custom data structures like hash maps to group positions and their chip counts, is also possible but unnecessary. It adds extra complexity and uses more space without providing any real advantage over the parity-based counting method. For this problem, simplicity and efficiency are key, so the parity-based approach is the best choice. Thank you for watching. In summary, we tackled LeetCode problem number 1217 by analyzing the problem's constraints and leveraging the odd-even positioning to minimize movement costs. This problem is a great example of reducing complexity by identifying patterns. Don't forget to like, share, and subscribe for more coding content. See you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!